Cool. Yeah. So I'm talking about learning constant depth circuits in malicious noise models. This is presented on behalf of my colleagues, Adam Kostis and Arsen from UT Austin, who unfortunately cannot make it to the conference. These slides are by Kostis, so if this talk goes well, I request that you give all credit to Kostis, and if this talk does not go well, I request you place the blame on Adam. Okay, great. So what is this talk about? It is about learning from contaminated samples in a broad model of contamination that captures what are known as malicious or nasty noise models in the literature. It's a fairly strong model of contamination. In particular, we're working in a supervised learning setting where you first assume that a clean set of IID samples is drawn from some distribution. Here we're going to focus on the distribution being the uniform distribution over the hypercube. Okay, and then an adversary gets to contaminate the dataset as follows. First, they get to remove an eta fraction of the dataset, and then they get to replace them with arbitrary adversarial data points. And notably, in this contamination model, the adversary gets to corrupt both the features and the label of the corrupted samples. So this is sort of a generalization of the popular agnostic learning setting where the adversary only gets to flip the labels. So here you also get to flip the features as well. Okay, so the goal in this model is we're trying to learn an output hypothesis on the distribution, which has misclassification rate at most 2 eta plus epsilon, where eta is the contamination fraction. And it's known that sort of this goal of 2 eta is unavoidable, so this is the best we can do up to this additive error of epsilon. Okay, so this noise model encompasses several noise models that were proposed in the literature, including these historical works, which propose things such as malicious noise and nasty noise. This work focuses on the particular setting of learning a polynomial-sized DNF, aka a depth-2 circuit, over the Boolean hypercube. And notably, even in this fairly simple setting, no quasi-polynomial time learner was previously known under this sort of strong noise model where you're able to contaminate both features and labels. Okay, so in the agnostic learning setting, where you're allowed to the adversary is only allowed to contaminate labels, a seminal work by Lineal, Mansour, and Nissan gave a quasi-polynomial time algorithm for learning constant depth circuits. So this is sort of like our benchmark in this problem setting. And what was this LMN algorithm based on? It was based on the fact that there exist low-degree polynomial approximations for constant depth circuits over this uniform distribution. So it was based on sort of these polynomial regression algorithms as well as like moment matching ideas. Okay, but notably, in this malicious or nasty noise model that is studied in this work, it is much more challenging because, in particular, contaminating some fraction of the features can completely violate this approximation property over the hypercube because you're changing the base distribution, right? Okay, so conceptually, this work is the first to overcome this challenging issue and gives a quasi-polynomial time algorithm for learning constant depth circuits over the Boolean hypercube when an eta fraction of features and labels are corrupted. So essentially it matches this element algorithm under this stronger contamination model. And yeah, as noted, no previous algorithm was known to achieve this rate. Okay, so I'll tell you a little bit about the approach used by this work. So recall that the key concern with applying the element approach is that these polynomial approximations may no longer hold once I mess with the distribution in total variation distance. Right. So how do you overcome this issue? Right. So you can't just naively use polynomial regression because the distribution has changed. So instead, the idea is we're going to try to find a subset of the examples that were given, such that the polynomial approximation property does hold, while not removing too many examples that we can learn from. So this idea is inspired by sort of these unsupervised techniques in robust statistics. Okay. And why is this possible? It's because that these low-depth circuits have the property of this that they admit sandwiching polynomials over the Boolean hypercube. In particular, this is a stronger notion than simpler things such as L1 or L2 approximation of by polynomials. Okay, so what is the algorithm? In a nutshell, this is the entire algorithm. So you first find, it basically proceeds by using a filtering step followed by the element sort of style polynomial regression. So in the filtering step, the idea is we're going to repeatedly find non-negative polynomials with low expectation under the uniform distribution. This is something we can compute because we have access to the moments of the uniform distribution, but have high expectation when evaluated on the samples. So in essence, this polynomial is supposed to be like a distinguisher between the data set you're given and the distribution that you can learn from, right? And you keep on doing this until no more polynomials can be found. And the guarantee of this filtering algorithm is that you don't remove too many clean points, namely that the points that you're removing from the data set are primarily due to the adversary. And at the end, because of the termination criteria, the guarantee is that the expectation of any non-negative polynomial has low expectation under the uniform distribution, which is the distribution you actually care about learning the function in. Okay, yeah, so as I mentioned, this sort of broad paradigm of filtering until some criteria is met and then applying the resulting clean framework on the data set is inspired by a long line of works in unsupervised and supervised learning. And here the sort of criteria we use is or that the authors use is preserving expectations of non-negative polynomials. Okay. So let's see how to put these steps together for the particular case of load-up circuits. So it's known that load-up circuits over the Boolean hypercube admit what's known as sandwiching polynomials with respect to the uniform distribution. In particular, there are low-degree polynomials that p down and p up that sandwich f star, such that p up and p down have very close expectations under the uniform distribution. Okay, so we're going to keep on applying this outlier removal procedure, and the polynomial we're going to use as a certificate is the difference between p up and p down. And note that this polynomial is always non-negative, right? And the point is, at the end of the day, we're going to have a data set where p down actually does approximate f star over the samples. So this sample distribution is not going to be the uniform distribution, but nonetheless we fixed this main issue I mentioned before, where polynomials do not approximate the true function that you care about learning. So this is good enough. Okay, and the point is that when you compare the error achieved on the samples to the error achieved on the clean distribution, it's very close because you've preserved most of the clean samples, and this is good enough to give you the final error guarantee. Yeah, that's the sketch of the analysis. By the way, I highly recommend reading this paper. So the paper is like only 10 pages long, and it has very clean, crisp ideas. So a quick shout out to reading the paper. Okay, cool. So as a quick recap of what this work does, it conceptually breaks this issue of feature contamination by showing that you can combine these outlier removal techniques with polynomial regression algorithms. And notably, it uses this notion of sandwiching approximators combined with linear programming to actually implement this filtering step. Okay. So you might be wondering, like, why am I giving this talk? Beyond the fact that I sit down the hall from these guys, so it was very easy to convince me to come give this talk. We have a subsequent work which sort of pushes the limits of this overall paradigm and shows, among other things, that sandwiching polynomials are sufficient but not necessary for this framework to go through. In fact, you can actually just give a similar guarantee for L1 approximators, which is a much weaker notion. You don't need this non-negative expectation preserving. And also, it continues to work under stronger notions of contamination, where you can replace a majority of the data set, not just the bounded eta fraction, with arbitrary samples. So yeah, the subsequent work is a little bit longer and more complicated, but it really illustrates the full power of using these sorts of techniques in conjunction. Thank you.
That was very nice. So what about like other things like intersections of half spaces where there are low degree approximators but perhaps not sandwiching?
Yeah, absolutely. So under this bounded contamination model, because they have L1 approximators, the algorithm continues to work. And under this sort of like heavy contamination model that we newly introduced, you actually do need sandwiching approximators. Unfortunately, it doesn't carry over. But there are a lot of like interesting open questions in this space.
Is your algorithm, it's not proper, right? It doesn't output.
No, it's not proper. It outputs like, the ultimate classifier is like side of a polynomial, similar to these
So
element.
even in the non-agnostic setting, it's still improper. Like LMN, it's improper.
So it's hard. Are there arguments also proper then?
Yang has things, so there's like a quasi-poly, and there's like a S to the log 1, yes.
So you can do something.
You can do something, but that's with queries.
Membership query.
With membership queries.
Yeah, hey, I'm wondering, maybe I missed it, for the subsequent work, does it completely subsume this work, or is there any?
Yeah, so I guess as it gives a general theorem. One of the special cases of that general theorem is this work.
Any other questions? Okay, so let's thank the speaker again. Thank you. And okay, so our next speaker is Philip. Thanks. Okay, hi, yeah. So I'm Philip, hi everyone, and today I'll talk about the work Yihan Marco and I've been doing on multi-index models and spectral estimators for them. Right, okay, so without further ado, let's introduce what's the setting, what are multi-index models. So basically we're just in a regression setting, d-dimensional input, one-dimensional output, and what multi-index models postulate is that we're first actually doing a linear projection to a p-dimensional space that's strictly lower usually than D, so think of P as something smaller than D, and then we're doing some non-linearity, some link function. And why this has received renewed attention recently is due to its connection to two-layer neural networks, right? You can see just immediately how this models it. And the questions we were asking in this work roughly was how many samples do we need in order to say anything about the weights W star of this between the in the first layer, right? Okay, and then because we want to formalize this, we need to make some assumptions, certain assumptions on the model. And the assumptions we're making is that our input data is going to be Gaussian. And very importantly, we're assuming a linear regime. So basically the ratio between the number of samples and the dimension is kept fixed at delta. Okay, and so we're also letting both the number of samples and D go together to infinity. On the other hand, we're keeping the P fixed, so you should think of P as something very small, and on the other hand, D as something very big. And the objective is to say something, so to weakly recover W star, given that we know what the link function is, so what nonlinearity is, maybe ReLU or polynomial functions, given n samples, and given the covariance of the W star. Okay, and to further just formalize what we mean by weak recovery, is that we just want to come up with a matrix W hat that whose rows, one of the rows just overlaps with one of the rows of W star. So we just basically want to say something, anything about the row of W star in a non-vanishing way when the D is going to infinity. And why this is maybe non-trivial is can be demonstrated by saying, okay, let's say that we just sample randomly our estimator W hat. If we just sample it randomly from the sphere, well, this is actually going to be 0. So we should come up with something that's just a bit smarter than doing something trivial. And in this case, what we were considering was using spectral methods. And what spectral methods are about is just using the input, so the input data, the x's, and using a function t, so the pre-processing function on the outputs, to kind of scale the importance of the inputs x, right? So we want to put more importance on the data that we suspect is going to correlate with W star and less importance on the others. Okay, just one intuition why this could make sense to even consider is if you're looking at the expected value of this matrix, and then we're because we're considering the top p eigenvectors of this matrix, if we just look at the expected value, we can notice that it's going to be a block matrix in the context of orthogonal, if our signals are orthogonal, right? And then in the case that we picked our preprocessing function in a smart way, well, the eigenvalues in the top block can dominate the ones in the lower block, and in this case, the outputs that we get could recover the signal space. So in this case, the first p just elements of the canonical basis, right? But this is just about expected value of the matrix. We are actually our results. We want to have something stronger. We want to do with almost sure convergence and concentrations. So this is just a heuristic argument why this could work. And actually, spectral methods have been already, have been considered in many other examples, but have been considered for single index models. So when p is equal to 1. And in this case, they were proven to be matching the information theoretic lower bound in terms of the needed sample complexity for a certain link function Q. Okay. So moving on, we go to the results that we obtained in our work, and that's for kind of generalizing some parts of this previous work, is there's a certain phase transition phenomenon happening. Basically, there exists a the critical threshold of delta C that tells us the needed sample complexity in order to say something about W star. So if we don't have this, if our sample complexity is below this delta critical, then no matter which preprocessing function we choose, we cannot achieve weak recovery. On the other hand, if we're above this threshold, we can achieve weak recovery, and we can exactly compute what this preprocessing function is that achieves this weak recovery. So just as an example, if we say that we're in the p is equal to 2, and then we have that our link function is just the product, well, we just compute this, right? For the people that are also familiar with approximate message passing, a recent work has considered when approximate message passing algorithm can improve upon non-trivial initialization, and they also get some phase transition phenomenon. And actually, for a certain case of link functions, these thresholds match. Yeah. So, but this was mainly for link functions that are permutation invariant and some similar conditions to that. Okay, but these results, very importantly, rely on getting the asymptotic behavior of eigenvalues and eigenvectors of the matrix D that we're considering, right? And this is the next, the important result that we got. And here, I just want to maybe take a step back because some things here are obscured, right? So I just want to focus on the equation here, in the connecting the matrix M and the function G, right? So here, matrix M and function G, you can just think of them as some certain functions that take a parameter alpha and spit out. So matrix M spits just out like a matrix, P by P matrix, and the function G just spits out a number, right? And we know what they are, but it's not necessarily important. We get into the details of how they behave. But the important thing is we have an equation that deals with p-dimensional objects as opposed to d, so this is kind of tractable. And if we solve this equation, and our solution is above a certain threshold, which is here C, then we can get a non-trivial overlap for when we're analyzing the eigenvectors of our spectral matrix. On the other hand, if there is no solution to this equation, then there is no overlap, and we cannot say, yeah, we have that this actually converges to 0. We have a similar result also stating this for the eigenvalues, but yeah, it's kind of the same flavor. But as I said, I just want to kind of explain, so this is the important equation, and I just want to explain, so it's not important what these functions are, but kind of how they behave. So the function g is at first just flat, and then it's monotonically increasing in convex. And actually where the threshold happens is when it goes from the flat to the convexly increasing, right? On the other hand, the eigenvalues of our matrix are convexly decreasing. So we have three options that can happen in terms of recovery. If the intersection happens above this threshold, so on the part where the g is increasing, this means that we actually get recovery. So in this case, our top eigenvector will recover one of the directions of W star. On the other hand, it can happen on the flat part. In this case, we have no recovery, or it cannot intersect at all also. In this case, we again have no recovery, right? So actually getting the result for where optimizing T comes from is that we can move around these red and blue functions, and in this case, actually, basically getting this threshold that we cannot find anything is just moving the blue function around so that there is no recovery. Okay, just simply to go fast through the proof idea, in the one-dimensional case, we connect the eigenvalues and eigenvectors to rank 1 perturbations through some tricks, basically. Then we use the asymptotic of the eigenvalues of rank 1 perturbations to get the asymptotic performance. And then just we can lift this restriction using free probability. What happens when we have p larger than 1 is that we actually need to come up with, just in the first 2 steps, with a different technique than using just the inverse of a function, because it no longer works in multiple dimensions. So we need to kind of get by, and this was the bulk of the work basically spent on, just coming up with a clever way of finding the fixed point equation and the matrix function that connects it to rank p perturbations. Okay, lastly, just to recap, we use this spectral matrix, we locate its top eigenvalues and eigenvectors, and then in the end, we optimize the pre-processing function in order to recover the matrix W star below the threshold, above the threshold and below. We prove that no recovery is possible. Thank you for your attention. Right, yes. Yeah, so, oh, yes, of course. So the question was, what's the relationship between the AMP threshold and the spectral threshold? So for basically when the link function kind of exhibits a behavior closer to the one-dimensional case, so kind of when it's permutation invariant, or a bit more complicated than that, then you get that they match. In the other case, the AMP threshold is lower than the spectral threshold. So, yep. Not, okay, so not that I am aware of, yes. Yeah, so in the P larger than 1 case, but I mean, yeah, just I'm not aware of it, yes.
I may have missed this, but here the exci's are Gaussian, right? Like
yes, exactly, yes, isotropic Gaussians.
I was curious if these ideas could help understand settings where maybe x comes from a log concave distribution or something, because I mean algorithmically we know that, you know, like Vempala and a bunch of other people have shown that with juntas on log concave distributions you can use PCA type techniques. So I was curious if you can use your ideas to get precise characterizations or better characterizations there too.
Right. So I think one of the properties we're using is rotational invariance of the distribution. So for these precise techniques, rotational invariance would be needed. So I think going just beyond that, maybe some of the stuff here breaks down. But right now, I think thinking in terms of just pushing this to rotational invariance would be the first step before going to the generalizing the result, right? So, yeah. So I think, yeah.
How do we go to next slide? Okay. Okay. Thanks a lot. So this is a talk on generalized linear models, and thanks, Philip, for already introducing multi-index model, because what I'm going to talk about is single-index model. So you already know the definition. So this is a joint work with my student Nami Matsumoto. I'd much rather have Nami give the talk, but for some reason she cannot travel. Okay. So as I said, this is what a generalized linear model looks like. You have covariates x, and you have features, or like you have labels y. They are sampled from some distribution. It's slightly more than a linear model. So expectation of y given x, which is a d-dimensional vector, and y is just a scalar. This expectation is linked with the linear projection of x onto some ground truth vector theta star. Right? So this is what is called the link function, this G inverse. So this is essentially the nonlinearity. So it's a slight generalization of linear models. That's why there's generalized linear models. So in this talk, we are going to focus on GLMs where y, or the level, is binary, so plus minus 1. So traditionally in statistics, it's a very well-studied model, and the aim is to find out this theta star. We are going to pose one other constraint on theta star, is that this is k-sparse. That means it's a sparse vector. It's actually a generalization, so if you just put k to be d, then it's the usual case. So this is a more general result, and there is a lot of reason why sparsity is sort of imposed over here, and I'm not going to, I think, given the crowd, I'm not going to go over that. So this is our data generation models. So what we are going to do is parameter estimation. That is, we are going to recover theta star. In this case, we are going to assume that theta star, since this is theta star is a unit vector, and we will estimate some theta hat over here. Sorry, theta hat over here, and we are going to measure the Euclidean error. So that's going to be called error rate. D is the parameter dimension, K is sparsity, K is usually much less than D. N is the number of samples, so that's the number of times we are getting to see this. And we will be coming up with an algorithm so that we get this theta hat. So it's same as the previous talk. We will not assume the knowledge of the link function as well. So since this is binary outcome, without loss of any generality, we can just write the output of the GLM or the y vector as just a function f, which is a random function. So this actually is +1 with probability p of z. So in pz is the proxy for link function in this binary case. And with probability 1 minus pz, it is -1. Okay, and again, we, for technical reasons, we will be sticking to Gaussian covariates. So x1 up to xn are all Gaussian. So they're IRD, white Gaussian. So this is y equals to f of this thing. So that's our model. Great. So for this binary case, it's pretty well motivated. There are a large number of classification models, and these two are probably the most popular. Logistic regression, which falls under this, where PZ is given by this sigmoid function, as you all know. And for the case of probit regression, which is a similar model, the P function or the link function of the GLM is given by the error function or the Gaussian CDF. Okay, so these two are popular examples of the model that I'm considering. And I'm doing parameter recovery under this model. The algorithm that we are going to use is called binary iterative hard thresholding, or BIHT. So what it does is something interesting, and that's going to be our main, the main body of the talk. It's basically a gradient descent type algorithm that starts with an arbitrary theta hat 0, and then goes for a number of steps. In each steps, it updates the theta vector by adding this quantity, which is gradient of something. We'll see what this thing is gradient of. But what this is doing, it's actually, it's just checking whether the sign of your current prediction match with what is there. So yi versus whatever your sign of, x transpose theta hat t minus 1. So if they match, then there is no update because they cancel each other. If they don't match, then you take the corresponding covariate x and add it, right? So it's just like a batch version of the perceptron with some learning rate over here, which is square root of 2 pi, if it has been done to enforce something. So it's just a badge version of the perceptron algorithm that we are going to use. And then this is simply a projection thing. So since we mentioned that we are going to do a sparse recovery, or we are imposing this k sparsity thing, we'll just do a top k thresholding. We'll just take the top k coordinates and then normalize it. That's our algorithm. Okay. So I mentioned this is so this has been used in the context of 1-bit compressed sensing. It's called so there is a precedent of this which is called iterative hard thresholding for compressed sensing. It's been around for the past 15, 16 years. But as I said, this badge version of perceptron, so it's been around for way longer. Okay. Right. So what is this thing? This gradient is the gradient of. That loss function is the ReLU loss function. So it's max of these two quantities, 0 and minus y x transpose theta. So that's the ReLU loss. You see, when we take theta to be 0, the value of the loss function is 0. That's why we had to impose some regularization when working with this loss function. That's why we are normalizing. We took theta to be unit norm, and we have normalized it. So this is actually a subgradient of that ReLU function. So I wrote it in the matrix vector notation, but it is basically the simple thing that I just mentioned. Okay, so there are some interesting properties of this ReLU law. So we want to show, like, it has been an agenda of Nami and I. We had 2 or 3 papers on these topics where we are trying to show that BIHT is robust for a wide range of non-separable data. And this GLM, logistic and probit regression, and so on, they're actually example of noisy data, noisy classification problems where data is non-separable by a half space. So what we are basically showing in all of these cases that BIHT is robust and it leads to information theoretically optimal sample complexity for parameter recovery in a pretty large, pretty wide setting. For this particular talk, we are concentrating on binary outcome generalized linear models. And the added sparsity constraints are basically showing that even with this severe non-convexity, gradient descent on ReLU loss is powerful enough to do very good parameter, like information theoretically optimal parameter recovery. Okay? See, I think I'm not speaking into the mic properly, hopefully. But I'm used to, like, being from a state school, I'm used to really big classrooms where I have to throw my voice. I hope you guys could all hear. Oh, okay, you're recording it. Then I'm in trouble. So then I have to tell why the students cannot travel now. And okay, good. So a lot has been done in GLMs and also in particular to binary GLM. So I'm not going to go over this setting, but there is like various sample complexity thing. And what we are claiming in this 10-minute talk that we are sort of improving over a bunch of previous work. So that includes AMP and like there is some work by like Trampolidis and so on. There is also work, a spectral best method for this problem, as you have heard. Okay. So there are a couple of properties of the link function that is going to come into picture when we are showing our result. So one property is the amount of noise. So this is probability that random function fz is not equals to sin z. So so how far it is from being a half space, right? How non-separable it is. So you can actually find that probability. So that would be for logistic regression. For logistic regression that was pz. So conditioned on z, this is actually going to be the curve. You integrate this curve to get something like alpha. So you can calculate this out. Also, we need to know what is the average slope of this PZ. That is, since we are assuming Gaussian covariates, this, like, even if it were not Gaussian, this is from Stein's lemma. This shows up to be the slope of this function, but it is not really the slope. It's usually that expectation of z fz. Okay, so we can actually, like, I don't think I have time to elaborate on these two quantities, but those are essential in our result. So here is the theorem. The theorem says that if couple of assumptions are true, that P is non-decreasing, and something happens, which is again properties of that curve that I was just showing, then when you have this number of samples, max of alpha, and we call epsilon is the error rate, alpha is the amount of noise, gamma is the slope of the link function, then you need k log d over k times that quantity, order of that number, you use that amount of sample, then you will get estimation error epsilon. So that's the sample complexity. This not only that, we have very fast convergence rate for BIHT. Okay, so this is like how the error varies in over Tth iteration. As you see, as t goes to infinity, it's super linearly, like super linear in optimization parlance. This will converge to the actual thing. So if you are getting rid of the sparsity thing, then that k will be replaced by d, and you get the same thing with d, right? So this is without sparsity. Same result is valid. Now, why did we say that this is information theoretically optimal? Because for logistic regression and probability regression, the minimax rate was given very recently, actually, only, yes. Oh, okay, I'll just wrap up after this slide. So, so that was given recently, and we are actually, if you just plug in for logistic and probate the values of alpha and gamma, you'll match this result. This is something from the last cold by Daniel Su and me. Okay, and it's in practice also pretty good. I wanted to tell, okay, if we have a large amount of time, I would have told you how it actually works. But I will just let you, I will just end it with a final comment that normalization step, when the noise is small, it turns out that is not necessary, but as noise is increased, it becomes really necessary. So we have not been able to figure out why that happens. And with Massart noise, BIHT is really good empirically, but we cannot prove it yet. So if someone can do it, that's great. Okay, that's all.
Maybe we have time for one quick question, otherwise let's take other questions offline. Anyone?
Thank you so much. A very nice talk. One question that I have is more, maybe not exactly on what your contribution is what's the relation between the link function and the modification of gradient descent that you have with the sign? It's more maybe a...
Right, so our algorithm is oblivious to the link function. I have not used it, so the link function has to satisfy some properties. And the properties are quite, minimal. So one is it has to be non-decreasing, like the logistic thing, it keeps on like sigmoid function. The other thing is away from margin, it's growing slower. So it becomes more flat away from the 0 point. So those two things, if they are satisfied, then this is going to work.
I see. Okay, thank you.
Okay, so let's turn the speaker again. And our next speaker. Okay, so next speaker is Apoor Vikram Singh. Welcome, Apoor.
Hi, I'm Apoor, and I'll be presenting our work on sharper bounds for Chebyshev moment matching with applications. And this is a joint work with Cameron Musko, Christopher Musko, and Lucas Rosenblatt, who is sitting there. Okay, so I want to begin by introducing method of moments. So let P be some unknown probability distribution, and let it be bounded between the support is in -1 to 1. And now you're given noisy moments of P. So where the jth noisy moment is just some integral x to the power j, P of x dx, plus some additive noise. And your aim is to estimate P in Wasserstein-1 distance. So given an epsilon and some noisy moments, output a distribution Q, which is close to P in Wasserstein-1 distance. Let me define Wasserstein-1 distance. So it's just the largest difference between expected values over all one Lipschitz function. So I'll give you like an intuition for this. So if P and Q are close, then you would expect expected value of f of x when x is coming from P should be close to expected value of f of x when x is coming from Q for well-behaved functions f. And Wasserstein one distance just says that it should be close for all one Lipschitz functions. It also has an earth movers perspective, but I'm not gonna need that for this talk. Okay, so the question I want to ask is how much noise can we tolerate in the moments, right? So Kong and Valiant gave an algorithm, and Jin, Muse, Sitford, and myself, we gave a matching lower bound, which says that you need to estimate first 1 over epsilon moment to accuracy exponentially high in epsilon. I want to give a quick intuition for why that is the case. Now imagine two probability distributions P and Q, most of whose mass lies between 0 to half. Now let's compute the jth moment of P or Q. So I've written the jth moment of Q. You see that it is already less than 2 to the power minus j. So to be able to distinguish them, you'd need to estimate them to accuracy exponentially high in epsilon. Okay. So are we doomed? Like, what if we could integrate? You can see the picture here, right? Like x to the power j is a terrible function. What if we could integrate with something better? So towards that, I want to introduce Chebyshev polynomials. So the ith Chebyshev polynomial is just a degree I polynomial, and it's denoted by Ti. And we define it recursively. So T0 of x is 1, T1 of x is x, Ti of x is 2x, Ti minus 1, minus Ti minus 2. It looks like this. So I've plotted T10, T11, and T12 for you. Now for the P and Q, as in the previous picture, you can see that if you integrate T10 with P, it would be much different than the integral of T10 with Q. So we have something. So formally, the jth Chebyshev moment is denoted by Tj of P. It's just integral of the jth Chebyshev polynomial times P of x dx. And at this point, I want to note that for most applications, it is as easy to estimate the Chebyshev moment of a distribution as it is to estimate the monomial moments. And Braverman, Krishna, Musko showed that if you estimate the jth Chebyshev moment to additive error plus minus epsilon for first 1 over epsilon moments, then that suffices to output a distribution Q which is close to P in Wasserstein distance. Okay? And our result implies that you can make more error in estimating the higher moments. In particular, if estimating the jth Chebyshev moment to accuracy root j times epsilon suffices. Okay? To some, it may not seem like a lot, but since it is such a ubiquitous problem, we immediately get like a bunch of applications out of it. So I'm just going to flash these numbers to you. I won't go deeply into it. So we show for the problem of estimating eigenvalues of matrix using matrix vector products, we improve the bound of order 1 over epsilon square matrix vector products to order 1 over epsilon matrix vector products. We also give an efficient algorithm using this for generating differentially private synthetic data, which is close to the original data in Wasserstein one distance. And we improve the bound on Wasserstein one distance. And we also tighten results of Vinayak, Kong, Valiant, and Kakre for estimating population of parameters. So we just improve their analysis by chugging in our bound. So the upper bound of n to the power 0.22 improves to n to the power 0.25. Okay. So yeah, I told you this doesn't mean anything, but okay. Now now the main thing I want to show you is like, why can we afford lower accuracy in higher moments, okay? So I've plotted T50 for you, okay? Now imagine P and Q, which are quite close to each other. Now in this case, the 50th Chebyshev moment of P would be much different from 50th Chebyshev moment of Q, even though they are quite close to each other. So higher accuracy in higher Chebyshev moment doesn't matter. Like if P and Q are already kind of far, their 50th moment would be much further. So you can make more error in approximating the 50th moment or like higher Chebyshev moment. Okay. So now I'll state our result formally. So let P and Q be two distributions and K be an integer. So K would correspond to the number of moments I'm interested in. Okay, let me parse this for you. It says that if the difference of the jth Chebyshev moment of P and Q divided by j the whole squared and sum that from j equals 1 to k is less than some quantity gamma squared, then Wasserstein one distance between P and Q is c over less than c over k plus gamma. So like there's an inherent trade-off. Like if you choose k to be very small, then c over k term would be big, but you might be able to control the gamma term and vice versa. In particular setting, k is equal to 1 over epsilon, gamma is equal to epsilon, you get Wasserstein distance to be, if gamma is epsilon, then Wasserstein distance is order epsilon. I want to give you like a quick proof sketch of this. So let's recall the definition of Wasserstein distance. And the main idea is to represent this one Lipschitz function, f, as a sum of Chebyshev polynomials. So it's an infinite series, and you can represent that. And a famous result in approximation theory says that if you just truncate this infinite series to just k plus 1 terms, so now fk is just a degree k polynomial, and that fk is a good pointwise approximation to f. So now you do the usual trick of writing f as f minus fk plus fk, and because f minus fk's infinity norm is small, you'll be able to bound this term to c over k. So that's how you get the c over k term on the theorem. Now the main thing of interest is the second term. And after some calculations, you can show that this is just Cj times the difference of jth Chebyshev moment of P and Q. This is the quantity we are interested in seeing how we can control it. But if this is less than epsilon, so okay, sorry, the folklore result says that Cj is order 1 over j. So if this thing circled is order epsilon, then we recover the result of Braverman-Krishna-Musko. But in this paper, the main thing we prove is like a better bound on Cj. So in particular, this is the theorem that f be a one Lipschitz function representing the Chebyshev basis. And now if you just sum j Cj the whole squared from j equals 0 to infinity, this thing is less than equal to 1. In particular, it implies that Cj is order 1 over j, but we have something stronger. And then just applying a Cauchy-Schwarz inequality to this thing, this particular term is less than gamma, and the first term is less than 1, and you get the proof of the theorem. Yeah, I guess that's it. Okay.
Any questions?
Yeah, so nice talk. I guess one thing you mentioned is that for a lot of applications, it's easy to match the Chebyshev moments just like the monomial moments.
Yeah.
Could you give some clarification when you can expect that to happen? Because I guess on one hand, the coefficients are growing exponentially. On the other hand, you gave many applications, so I believe you. I'm just curious, sort of, when it works.
So I think like the main property of Chebyshev polynomials you use there. Okay, this is way too slow. But like Chebyshev polynomials are bounded between -1 and 1 in the range -1 and 1. So basically, you don't really care about the coefficient growing. It's the size of the moment. So that doesn't grow. Yeah.
Can you say anything about the quality of moment matching algorithms when you measure them in WP for p greater than 1?
Possibly offline, but not now. Yeah, like there are some conditions where this one would like you can nothing non-trivial like this. I guess like whatever you can get out of one, you just plug that in. Yeah.
Thanks.
Okay, so maybe one more question from me. So, is there a converse to your technical results? So you showed that any one Lipschitz function
Oh no.
very fast decaying representation in terms of Chebyshev.
Yeah.
So does your result apply to any function that its representation in terms of Chebyshev decays fast enough?
Basically, are you asking like if function satisfies these, are they one Lipschitz?
No, this or if your result applies to this property more generally.
Yeah. I mean, it would apply to this property more. This is
Function that has a
fast decaying. Yeah. That would be yeah.
let's bring the speaker again. Our next speaker is Mohsen. Sorry, Christian. No, let's not next speaker. You're Mohsen, right?
Yeah.
Okay. So it's not the right talk. Or what would be easier to switch the speaker or the slides?
This work talks about learning DNF through a generalized Fourier representation. And this is a joint work with my colleague, Ronnie. Boolean Fourier expansion has been a fundamental tool in analysis of Boolean functions. It says that any function on the Boolean cube decomposes into a linear form where the coefficients are called the Fourier coefficients. And the basis element are nothing but just parity functions. And this tool has been studied with numerous applications in learning theory, property testing, noise sensitivity. And over the past few decades, there have been a lot of learnability results for classes of Boolean functions. And however, despite all this progress, this Boolean Fourier is limited to uniform or product probability distributions. And our focus is to generalize this Fourier expansion and also looking into the learning aspects of it. And the learning model we use is a standard membership query model, where it's similar to a pack learning model, but the learner can do membership queries to an unknown target function. And the learner is asked to output a hypothesis H such that it agrees with F most of the time under the probability distribution D. And a simple example is a 20-question-like game where Alice tries to reconstruct the Bob's function. Maybe Bob's function is a DNF, and Alice tries to ask questions by fixing some input assignment of her choosing. So learning DNF has been studied a lot. There are some hardness results. And the best known algorithm is known to be not polynomial. There are efficient learnability results for certain subclasses of DNFs, including monotone and log n-term DNF. There are also efficient learnability results under distributional assumptions, including uniform and product distributions. And learnability, efficient learnability under non-product distribution has remained open for more than 10 years. And this is a problem we are focusing on. Okay. And our first contribution is development of a generalized Fourier expansion. And the key concept here is a Bayesian network connection. So a Bayesian network is nothing but a directed acyclic graph where the nodes are random variables. And we have the probability distributions that sits at each node. And with that, we define a Bayesian-induced Fourier expansion where the parities are looking like this, where mu's are the expectations, sigmas are standard deviations, and now we prove that this is an orthonormal basis, hence we get a Fourier representation. And of course, this subsumes the Fourier under product distributions. And we look at properties of this Fourier. It has the standard properties, but it has a key difference, which is that it does not impose a sparsity. So under the uniform Fourier, if you have a function that only depends on t variables, we expect that the Fourier coefficient to be 0 for the subsets outside of t, but this does not hold for the Bayesian-induced Fourier. So this picture probably tells you the story. And for the learnability of DNF, which is our second contribution, it turns out that a spectral norm plays an important role. A spectral norm is nothing but just L1 norm of the Fourier coefficients. And Feldman and Cole 2012 showed that if the spectral norm of conjunctions of size D is bounded, then STEM DNFs is learnable. And this is under uniform or product distribution. So our result is to extend this to arbitrary distribution D. And the idea is to use the PTF construct of Feldman plus an extended version of the KM algorithm. But we still need to prove that a spectral norm under this new distribution is bounded. All right, so this is the extended KM, so which is more or less similar to the KM algorithm. And for those of you who don't know that, KM is a recursive algorithm that finds the heavy coefficients of a Boolean function. And, all right. So with these in place, we get the learnability if we can prove that spectral norm is bounded. And most of the paper now deals with this issue. We look at D-literal conjunctions, and we need two distributional assumptions. One is C-boundedness, meaning that the probabilities are not too close to 0 or 1. We need alpha difference bounded, meaning that in a Bayesian network, the parent cannot dictate too much to a child node. So meaning that the difference of expectation and standard deviations can vary at most by alpha if the parent's realization changes. And we prove that when alpha is less than half, we get nice upper bound on the spectral norm for chains, for trees, and as a byproduct, we get an improved upper bound for product distribution, and also an exact characterization of the spectral norm. And this is the main idea. We look at a very simple function. And the key challenge here is that, as I mentioned, the new Fourier expansion does not hold sparsity. So we need to address this issue. And this is a simple one conjunction on a chain. And if the distribution was product, the Fourier spectrum would look like something like this. It's always 0 except 1 point. And for chain, we prove that if alpha is small enough, it decays exponentially. And that's a key component in our analysis. For D conjunctions, the idea is basically to decompose the chain into multiple segments, and we study each segment separately. And for Bayesian, for 3 Bayesian networks, we decompose the tree into branches, and then we handle the multiple branches coming to the same parent. And one question is this alpha really a fundamental constant here? And the answer is yes. We prove exponential lower bounds when alpha is not bounded by half. For general graph, unfortunately, we don't know the answer. If alpha is less than half, we can still get exponential lower bounds. And as a byproduct, we get learnability of DNFs under K-Munta distributions. I'm going to skip the details. And to conclude, we had proposed a generalized Fourier representation for Bayesian networks. And we showed that these KM algorithms and other algorithms can be generalized to arbitrary distributions. And as these are the future works, I guess I don't have time to talk about that. Thank you.
Yeah, so am I right to understand that this is saying that you can use the Bayesian networks to basically model any distribution and then get your Fourier representation from that?
Right.
Okay.
Right. But the learnability results so far holds for 3 Bayesian networks that are also difference bounded.
Okay, cool, thanks.
Yeah.
What kind of function do you output in the end?
So it's the same type of functions that Feldman outputs. So it's a sine of So we do estimate the Fourier coefficients, and then there are some adjustment for the range of the function to ensure the range of functions stays between -1 and 1, and then we take the sign of that.
It's like a sparse according to this Fourier basis, and then you click it in somewhere.
Correct.
Okay. Our next speaker is Puchian.
Hi everyone, my name is Puqian Wang. Today I'm going to talk about our work on robustly learning monotone generalized linear models. So suppose we are given a bunch of data x and y, where x is a d-dimensional feature vector and y is a real label. Generalized linear models assume that the labels can be captured by an activation sigma composed of a linear function of w star times x plus some noise. Here, under GRMs, we assume that activation sigma is given a priori and comes from this large activation class big F. And we further assume that this unknown parameter W star has bounded norm. And our goal is to find a vector W hat that minimizes the L2 squared loss. GRMs have a wide range of applications. For example, you can view it as a training a very baby neural network that contains only one neuron, which is a fundamental in machine learning. And it also finds applications in statistics and economics, etc. So in this work, we are considering a large activation class where we wanted to learn any monotone and B-Lipschitz activation. This is a very fundamental model that includes most commonly used activations ranging from values to sigmoid and to this kind of weird functions, that is monotone. And furthermore, we are considering the challenging agnostic noise setting, where under the agnostic noise, the adversary can manipulate the labels arbitrarily. And essentially, this means that we make no assumptions on the label y. Now, let opt to be the minimum L2 squared error that you can achieve, and let W star to be one of the vectors that achieve this minimum L2 squared error. Our goal is that under some proper assumptions, we want to find the vector W hat that achieves L2 squared error of at most c times opt plus epsilon. And this c is an absolute constant. And by absolute constant, it means that it should not depend on the dimension d, should not depend on the activation sigma, and all those kind of parameters. So in other words, we are, instead of trying to find the best hypothesis, we are trying to find the hypothesis that is comparable to the best. And in fact, this is the best we can do. Because prior lower bounds have implied that distribution assumptions and assumptions on the activations are required for polynomial time algorithm. And this kind of error guarantee of c times opt plus epsilon is in fact the best we can hope for polynomial time algorithms. GRMs have been studied for a long time. In the realizable or in the setting where you only have simple additive zero mean noise, this prior work, KKS11 from a decade ago, have already provided an efficient algorithms that can learn all monotone and B-Lipschitz activations under very general distribution assumptions. Unfortunately, the algorithm only works for realizable or the zero mean noise case. So since then, people have tried to extend this result to agnostic setting. However, in the current thread of research in agnostic setting, there are two main flaws. The first one is that most of these algorithms only work for a very restricted subclass of the monotone and Lipschitz activations. In particular, they can only deal with activations like values, leaky values, those kind of activations that have large growth on the positive side, or have bounded slope of the activation. So, and in particular, they fill for many other important activations like sigmoid or biased value, etc. And furthermore, all of these prior works only obtain suboptimal error guarantee in the form of this, where this factor c of sigma prime is in fact not an absolute constant, but some constant that depends on the activation sigma or sigma prime. For example, in our prior work in 2023, when the activation sigma is chosen to be sigmoid, we have this parameter going to infinity, therefore providing a very vacuous error guarantee. So in summary, in prior literature, even under Gaussian distribution, we have no efficient algorithm that can robustly learn this important class of GRMs. So our work provides the first algorithm that tackles this task. In particular, we show that for any known monotone and B-Lipschitz activation, we show that there exists an algorithm that draws polynomial number of samples and runs in polynomial time and outputs a vector W hat that achieves L2 squared error of C times opt plus ypsilon, where this coefficient, where this constant C is a universal constant that is independent of sigma, D, and W, and ypsilon. And in fact, our algorithm can extend to work for any monotone activations with bounded 2 plus zeta moment, where this zeta is any positive real larger than 0. So, even though GRMs look very simple, it turns out that it's quite hard to learn GRMs. Mainly, we fix 2 obstacles. The first one is that the L2 square loss is actually a non-convex loss. So as shown on this figure, even on the very simple activation and on the very simple distribution, the loss landscape could look like this, which is a non-convex loss. And what's more is that we are tackling the challenging agnostic noise, which is disastrous to the loss landscape. And you can show that a little bit of agnostic noise can add suboptimal stationary points, which means that the landscape can potentially trap your gradient descent algorithm near suboptimal points. And our algorithm tackles these 2 obstacles by using this so-called data augmentation technique. So what data augmentation did is that we inject independent Gaussian noise to the feature vector, with the strength defined by rho. And then we return all these augmented data points. So here's what our algorithm looks like. So first of all, we update the data augmentation at each round of iteration. Basically, we are trying to perform a variable data augmentation process. And then after getting this augmented data points, we calculate the empirical gradient of the L2 squared loss using this augmented data. And then we update step size eta, and then we run the remaining gradient descent step. In the end, we test and find the best vector. So why does this augmentation work? So let me provide you with some intuition. So first of all, our first key observation is that this augmentation actually smoothes the landscape of the loss. We make a connection to the famous Ornstein-Uhlenbeck semigroup. Basically, what Ornstein-Uhlenbeck semigroup did is that they smooth the function f by adding Gaussian noise and averaging out the landscape near the vector z. So if you smooth the activation sigma using the OU semigroup T rho T, and then you calculate the L2 square loss of the smoothed activation, then it holds that this gradient is exactly the gradient of the smooth L2 square loss. Therefore, this gradient is effectively smoothing the landscape. Our next observation is that data augmentation actually amplifies the signal from the gradient vector. And you can argue that actually the gradient vector that we have been using is approximately a maximizing vector field among a class of commonly used vector fields. And that has the largest correlation with the target parameter W star. And due to this, we have this nice gradient alignment property that holds. Effectively, it shows that this gradient vector aligns very well with the direction of W star minus W, which means that the gradient field would drag you towards the target parameter W star. So as long as we have this gradient alignment property holds for each iterations, then we will have linear convergence rate. And to guarantee that, our key observation is that by variable augmentation, updating this augmentation strength per each iteration, we can guarantee that gradient alignment holds for all the iterations. The last step is to show that in the region that gradient alignment fails, we already obtain a good L2 squared error. And this is done by bounding this error term, where we use the staircase function phi to approximate the sigma, the activation sigma. quickly to sum up, we use this augmentation to smooth the landscape, and then augmented gradient vector amplifies the signal. And then using variable augmentation, we are able to make the gradient alignment hold for all the iterations. And finally, when gradient alignment fails, we get an optimal C times O plus Y vector. Finally, the last slide is that some future directions. The first one is that whether we can extend these results to general marginal distributions. And secondly, what about the setting where the target activation sigma is unknown to us? And in fact, we have already shown in our latest manuscript that this is indeed possible to learn. And finally, we want to see if there are any further implications to learning broader neural network families. That's all. Thank you.
So we have time maybe for one quick question. Anyone want a quick question? Okay, so let's thank the speaker again.
All right.
Okay, so our next speaker is Robbie Bhattacharjee.
Yeah.
Did I pronounce it correctly? Welcome.
Hi. So I'm here to present some joint work with my co-authors Caroline and Ulrike, my advisor, and we're from University of Tübingen. So our work is about what the title says, which is we want to figure out how to discard features based on SHAP values. So SHAP is a really popular local explanation method. People typically use it for tabular data, but I've seen it applied all over the place. And in a nutshell, the way it works is for a function, typically real valued function, and in our setting, we'll take it over some distribution mu. SHAP computes d SHAP values, one for each feature, that roughly tell you how important each feature is. I won't get too much into the details of what these mean right now. I can later offline if there's more time. So at a high level, SHAP works by essentially first considering the function by looking at all subsets of the d features. This is 2 to the d possible subsets, understanding the behavior of the function if you restrict to those features, and then aggregating all of that information into d SHAP values. And there's like a nice way to do that second aggregation step, and that's where this method gets its name, because it was discovered by this guy called Shapley. So in this work, we're interested in this local to global thing that people do all the time in practice. We found like, I don't know, at least 10 plus papers, especially in natural sciences, where the way people use this local attribution tool is they average it over the data set after taking absolute values to avoid cancellation, so that they can figure out what the important features are and what the unimportant features are. And I want to emphasize a lot of times in these applications, people are less interested in the final product of a model and more interested in just trying to understand the data. So it's becoming a common practice to like just train like an XGBoost model over your data set, apply SHAP everywhere, plot some histograms, take some averages, and try to understand the science of what's going on. So really natural question is this sound? Like SHAP wasn't designed with this in mind, but this is how it's being used. So this is the question we asked. Because intuitively, it seems like for a lot of practical cases this might work, but also sort of intuitively it feels easy to break this possible thing. So a little more precisely, what we'll say is we will say that a function is I invariant, where I denotes one of the features, if it doesn't change when you simply change that feature. Another way of looking at it is that if you just fix all of the other features constant, this fully determines the function's behavior. And maybe a more loose question you could ask is, if the aggregate SHAP value is close to 0, does this mean we're sort of close to an I invariant function? These are the 2 questions we'll be looking at. So I'm going to sort of just summarize the answer before I explain the answer. So in this work, we studied this question, and the answer is No, because you can obviously find pathological examples that mess up the SHAP values by having them appear as though some feature doesn't matter, when in reality you actually are using that feature a lot. But what we found that's a little bit more surprising is that if we slightly tweak SHAP, and instead of just looking at across the support of our data distribution, which is where the average is taken over, and we instead extend the support, which is something I'll explain in a second, then it turns out this method is pretty sound. And it turns out to be actually quite robustly sound, meaning that not only does exactly 0 mean we can discard the feature, but even being somewhat close to 0 means we can sort of just discard the feature in a fairly straightforward way. And based on this, we can just give a very simple modification to SHAP, where instead of applying SHAP and applying it, averaging it over the entire data set, you first decorrelate all your features. This is how you get the extended support, where basically all you do is permute every single feature column and then use the same algorithm. And we can show that this new algorithm has the nice feature of being sound and also preserves, I guess, some of the properties that SHAP might preserve. So I'll quickly get into why, as is, SHAP doesn't have this soundness feature that we want. And over here, I've plotted a function over this ellipse where f of x1, x2 is just the sum of x1, x2. And I've doctored this function outside of the support so that if you computed the first Shapley value, you would get 0 everywhere, suggesting that x1 is unimportant. And basically, the reason this happens is if you go into the details of how SHAP's computed, it samples across marginal distributions as opposed to doing conditional distributions. So this means to compute the SHAP value at that red point over there, you end up looking at all of these red points which clearly go off of the support. And this is what can mess you up. So basically, if I doctor the value of f on this red region, I can make the SHAP values essentially anything I want, thereby making the method useless. So this does motivate, though, our fix to the problem, which is instead of measuring SHAP just across this colorful region, we also add in this red region over here, which is actually pretty easy to sample from because all you have to do is just scramble your data columns, and now you have points from the red region. So this is what motivates the extended support. Oh, I think I've been not using the mic. Sorry about that. So this motivates the extended support, where the extended support can be defined by you take the marginal distribution across every feature, make them uncorrelated, and then take the resulting product distribution. Basically, pretend each feature is independent of each other and follows the given marginal distribution. So when we use the extended support and we re-examine SHAP, it turns out we get much, much nicer behavior. So I'll give our main results now. So the first thing we did was we checked when you aggregate these SHAP values over the extended support, do we actually get soundness? And the answer is yes, meaning that if you have a SHAP value for a feature I of exactly 0 for everything across this extended support, then you actually are I invariant, provably. Then what we did was we wanted a more robust version of this theorem. So we realized that if we additionally compute the SHAP value fully using the extended support, and by fully using, I mean that SHAP is a function that takes your data set and then outputs these values. So for the first theorem, what I'm doing is I'm using the original algorithm, but I'm examining it everywhere across the support. For the second theorem, I'm saying, wait, let's actually use the data you would get if you sampled from the extended support instead of the original data set. So this is what I mean by fully using mu star. So if we do that, then you can get a stronger guarantee, which is a aggregate SHAP value of at most epsilon means we're within order d epsilon from an I invariant function. And finally, and this is sort of a theorem that's I liked a lot because it's about a practical implementation of SHAP, which is that in most situations, if you recall at the very first slide when I showed SHAP, people use these 2 to the d possible subsets to compute it, and that's obviously intractable. So there's this method called kernel SHAP, which essentially tries to approximate how SHAP would behave across all those situations by learning a linear function. And this is what people actually use in practice. And it turns out our theorem applies equally well to kernel SHAP, where we have this extra eta term, which just determines how far away kernel SHAP is away from its limit behavior over the distribution. And if you ever play with kernel SHAP empirically, you find that it converges really, really quickly, which suggests that basically our second theorem directly translates to a practical algorithm. oh, those are two things I just said. Sorry about that. So I want to just emphasize what the practical algorithm I'm suggesting we use is. So right now, this is the general pipeline that people use, which is you first compute SHAP values over a bunch of points, then you average them, and you throw away the unimportant features. All I'm suggesting is we add an extra step, which is we permute each column of the data matrix, and then we do the exact same thing. So if you permute the data matrix, you actually get a new set of data that looks something like this, and now you just do the same thing, and this works great, apparently. So I have like 30 seconds left, so I'm going to sketch the proof in 30 seconds. Basically, if you write out what the SHAP values are, they look something like this. And these V sub S terms are the key things that you use. Basically, they're how you understand your function, S features at a time, where S is a subset of your D features. And the main idea is to realize as operators, these are linear operators, and they form together a solvable Lie algebra. Basically, when you play with these SHAP operators together, they have a lot of nice mathematical properties, and we can exploit them to find this algebraic structure. I also lied over there. I didn't mean simultaneously diagonalizable. I meant simultaneously upper triangularizable. That's why you need a Lie algebra instead of just having a commutative algebra. Anyways, that allows you to understand the invertibility of these things. And the last thing is that we can analyze kernel SHAP, because kernel SHAP essentially just changes these coefficients with some sort of garbage, but that doesn't actually change any of the structure of what's going on. And that's why our analysis carries over. And I think that's all I have time for, so thank you. No, so it's a good question. You kind of have to do that because SHAP itself assumes that the function is defined over a box. So, right. So I didn't define SHAP, but in the beginning, the way SHAP works is in order to try to understand how a function changes feature by feature, you first evaluate it all over the box. If you only stuck to the manifold, it's actually very difficult to figure out how impactful each feature is. That's how people use it in practice. Like the vast majority of times people use SHAP in practice, they're sampling over a box, and that's why people are using it for tabular data, which is where the box setting feels more reasonable. Yeah. All right, thanks guys.
Hello. Right, I know everyone hates me right now because I'm the last thing standing between you and an air-conditioned coffee break, so I'll try to make this fast. This is also a very long title. I will try to convince you within maybe less than 10 minutes why you care about any of this at all. This is a joint work with my amazing co-first author, Matthew, who's here, and our advisor, Morgan Olsen. Let's begin. So the reason why the sort of motivation into this problem is a question about data dependence, in particular data dependence that arise in a machine learning setup. So this is a very typical example in which the dependence arises in something called data augmentation. You've already seen that in one of the talks, but at a very high level, we are saying that when you are given a bunch of data sets, say a bunch of cat images, instead of training directly with these cat images, maybe you want to do some random transformations to them, such as rotations, reflections, color changes, and you want to train instead with this augmented data set. So this is more often motivated in ML engineering by some understanding of symmetries, invariants, how you want to encode certain robustness properties into your estimators. And it has very much become the staple in modern ML in both language and image data and so on. And people have various heuristic understanding of how it helps. Increasingly, people are also starting to understand why you may have unexpected or even negative effects of these augmentations in cases where you don't know symmetries. Or in one of my earlier PhD works with Morgan and my other advisor, Peter, we sort of try to understand the minute you go beyond low-dimensional linear estimators, how some of the negative effects will start to show. But at a very high level, what makes analyzing data augmentation difficult in an ML setup? It is because on top of having high-dimensional data manifested through super complicated estimators, you also have this notion of dependence introduced by, for example, randomly rotating the same image in your CAD data set. Right, so that's the mathematical challenge we want to tackle. And here you can see that in this data augmentation setup, dependence sort of shows up in a block way, in that you can just segment this data set into different blocks, and the different blocks are independent, but within each block of randomly rotated same image of the cat, you have all the dependence contained within there. This is not the only dependence setup that we study in this work. We also look at dependence that appears in a more general sense, for example, occurring time series or spatial data, where you are allowed to place your data in sort of a spatial field or along a rail line, and you have some sort of short-range dependence but long-range independent structure. I'm not going to details in here, but again, analysis of time series and spatial data becomes very, very tricky, precisely because you have all this dependent structure that's popping up in your data. Right. So if we do not care about dependence for once, and we are just caring about analyzing high-dimensional data in the kind of context of ML-based estimators, there's actually quite a lot of modern tools that are being developed that could help in this case. So one of this is what's called Gaussian universality. I'll make that precise in the next slides, but this is essentially a set of results that says, oh, when you analyze your estimators, you could pretend that all your training data are Gaussian, which sort of relates to one of the questions that's being asked in an earlier talk. And there's another set of techniques that says, if I know that all my training data are Gaussian, so if all the randomness are Gaussian, then I could use some sort of like Gaussian process-inspired kind of techniques to analyze exactly my optimization problem in terms of analyzing exactly, for example, the asymptotic test risk of my optimization problem. We are going to focus on what's called convex Gaussian min-max theorem, CGMT, which at an extremely high level is a set of results that says if you have complicated high-D Gaussian optimization, you could reduce it in many settings to simple low-dimensional optimization problems. I'm going to go into the literature of this and explain what these are in a sec, but these are all known results that are established over the past decade. Our contributions in this work is really to extend both of the tools to various forms of dependent data, such as the ones I've discussed just now. We use that to study the effect of data augmentation in a high-dimensional classification setup. We did focus our universality results only on high-dimensional logistical regression. However, the proof techniques we've built here, we expect that to extend to more general problems. And for step 2, this risk analysis tool, we developed a version of CGMT that works more generally for dependent data for beyond logistical regression. All right. So for the rest of the 5 minutes, I'm just going to unpack a little bit what Gaussian universality is and what CGMT is, for those of you who haven't seen it before. So Gaussian universality is this set of really this probabilistic phenomenon that says for many choices of statistics F, even for ones that are rather high dimensional, if I want to understand the limit of the statistics as a function of my data x1 to xn, say some distributional limit or mature limit, often I can replace my training data directly by Gaussians. And here by Gaussians, I mean the set of Gaussian vectors that match my original training data in mean and variance. So central limit theorem is actually a very simple example of this in the low dimensional setup, right? Like we just say that, oh, average of data looks like average of Gaussian, and that's what gives us our Gaussian confidence interval and so on for the average. And there's a series of work in probability that has established this for nonlinear functions Fs from Rota, Chatterjee to Moselle et al. The really interesting line of work to, I think, the ML community really emerged over the past decade, especially over the past 5 years, where people have shown that for various estimators and models arising in ML in high-dimensional setup, if I take my F to be the training or test risk of these models, so again, this is still a one-dimensional output sort of statistic, then I can often replace my data directly by Gaussians, and I have the same sort of asymptotic risk. And that enables a lot of analysis, right? So the reason why this is useful is that if we are dealing with Gaussian data, as we've seen in some of the talks earlier in this session, then all that matters are the mean and variance of our data, right? In the case of dependent data especially, even if we have very complicated dependence, the minute you're dealing with Gaussians, then everything reduces to sort of a correlation analysis. And I want to clarify that there are recent works looking at universality results for dependent data. A lot of them are focusing on dependence across different coordinates, whereas they are still looking at sort of independent observations. We build results that basically work for dependence across coordinates of the same data, as well as across different observations. And these two dependencies sort of play rather different roles in an empirical risk minimization problem. And at the very high level, the main universality result we built are as follows. So we look at a logistic regression estimator with rich regularization trained on a self-data, right? So we have our input xi, the output label obviously depends on the xi's as well. And we look at the equivalent version where you replace all the input data by Gaussians. And we say that under regularity conditions, in this high-dimensional sort of limits and under various dependent structures you've seen just now, if all you care about is measuring the training or the test risk of these estimators, then the two problems are actually asymptotically equivalent. Right, so that's our first result. However, even if I'm dealing with this Gaussian training data, it's not that obvious how you can analyze this directly because because our estimator is parameterized by our training data implicitly through this complicated optimization. For logistic regression or more general problems, you really don't have a way to write the dependence on data out in closed form. And that's where this CGMT technique developed by researchers in Caltech from a decade ago become really, really useful. So at the extremely high level, this self-technique CGMT is saying that this is a bunch of convex optimization problems involving Gaussian data that can be rewritten in this form. And I'm not showing the algebra here, but the key is this is an optimization problem where the data really just shows up in this high-dimensional matrix in the quadratic form, plus a bunch of loss regularization dependents that can be treated as deterministic. And the vanilla CGMT result says, if this data matrix G is IID standard normal, so for example, independent Gaussian white data, then I can replace this optimization, the analysis of this optimization problem by the following one, which no longer involves a Gaussian matrix, but instead involves two independent Gaussian vectors. And I know this looks a little bit complicated, but just to sketch the intuition, this really comes from the fact that if you have ID Gaussian entries in that matrix, right, your rows and columns are rotationally independent. So the way the optimization vectors show up, W and U, they only matter in a sort of average sense. And the advantage of this is, in the original problem, you sort of have to care about the complicated spectral behavior of my data matrix and how that interacts with my loss and regularization term. In the second problem, I no longer have a high-dimensional matrix, and in fact, the terms in this loss are sort of amenable to law of large numbers of argument, and which, upon a careful derivation, you can reduce this often to a low-dimensional problem. So I think I'm out of time, but you can sort of expect what we did. What we did is essentially extend this whole framework to a case where you allow for dependent coordinates and dependent data. Right? The original argument was very specific to IID white Gaussians, but then we managed to obtain a reduction that's applicable, especially to data augmentation. And we did some analysis on data augmentation. And finally, I just want to end by saying that the application of our paper is focusing a lot on logistic regression with data augmentation, but we do expect a lot of elements of this to be applicable beyond this setup. So extremely happy to chat about this during the coffee break. Thank you.
So let's thank all the speakers again.